All right. Any questions? Schedule or other? Okay. We have a midterm exam on end of April this month. So I will circulate out how to exam today. Basically, it will be an open book during the class time. I spread out how to exam later. All right, and then ocean renewable energy. It was originally created by Sung-mi. I handed out to me and modified later. Today I'll focus on wind. And on Wikipedia, the renewable energy is a collection of sunlight, wind, and rain, and tide, and wave, and geothermal heat. In four important areas is electricity generation, heating, cooling, and transportation, also energy sources. So it's mostly related to energy. So the source of all the renewable energy is basically coming from sun energy coming from sunshine. So we are trying to cover the wind waves here. Also, there is a direct radiation, and also hydrological cycle for raining. And then Earth is also using, and then volcano and hot spring and rains coming to the dam to hydroelectric power system. And there is an ocean tide. And then heat inside the earth, deep inside the earth. See that there is only less than 1% of energy altogether. So wind energy source is basically coming from the sun. So all the size is big, you know. This is a byproduct of solar energy. Only 2% of sun's energy reaching the earth and converted into wind energy. So whole wind energy is only 2% of solar energy. And then what is this? The wind directions because of the heating in the first week. And then also circulation due to temperature difference that create our wind, also rotation of the earth. Similar to the current, water current, the wind is more faster and more dynamic. The basics are very similar. So in terms of graphics, the whole solar energy coming to the earth, and geothermal, wind, and global consumption is only, not only, but anyway, 15. The whole wind has a much higher energy altogether, but we cannot, we need to convert them. So that is the problem of global consumption. So this side is much difference. And only around the Korean Peninsula, you see that there's a Japan, Korean Peninsula, and China. So you see the wind blowing at January of year 2004, and you see that there are red part of wind. The high wind is in southern sea. So this is for the island called Jeju Island. So around this island is very good place for Korean wind power generation. That's why we have this is a place. Here is again the Jeju Island. So you see that there are several sites already for the wind energy such like this. This one is different. This one is here around because there are a series of high mountains in Korean Peninsula. That's why we have a smaller size, several of them. But once again, the wind quality, wind speed, or we call this is a wind quality, is good in ocean area, in southern part, rather than the mountain part. But this one is good because it is close by to the population and easier to installation. Why wind power? The cost is dependent on the technology and also economy. But usually, many people are saying wind power is cheaper than other systems. And the wind turbine has a trend over lightweight, lower solidity, flexibility, larger diameter. We already see this. And thanks to load relief. This is through the twist and flap coupling. We call this is a band twist coupling. Stability. When there is a storm, the wind is fluctuating and very high. And sometimes the blade is break because of high wind and overloads. That is the way to relieve that kind of thing. The old technology was to have a separate motor there to rotate the angle of attack so that it reduces the load to the blade. That we call the active control. But here is another new idea of passive control. So without using a special purpose motor. And this is a trend. So already old type in Europe, Asia, and North America. Now probably Asia is even now size. And then what is this? Young's modulus and then density. This is a material property of materials used for wind power system blade. How the wind turbine is working? They convert kinetic energy, the wind energy, kinetic energy in the wind into the mechanical power of rotation. So in inflow of wind, it rotate this blade, activate rotor and blade. So blade is rotating, and the rotor, the axis, then there is a generator here. So something like this one. Here, there's a gearbox that converts the slow speed of rotation and the high speed of rotation. Then there is a electricity generator there. And then electricity should be go to the home somewhere. Wow. And there is a axis of rotation. And this is a typical one. We call this the axis of rotation is horizontal. So we call this is a horizontal axis of wind power system. Turbine. And this is typical one, but there is also a vertical axis wind turbine too. There somebody, especially in smaller size, and also in the future maybe bigger size, can be vertical axis. But currently we already see this one before. The size increasing. So now it approach megawatt, 10 megawatts, and diameter of 180 meters, very big. See this, I mentioned that this building is 6 floors. How tall is it? Okay. Larger.
6 floors.
6 floors.
18 to 24 meters.
30.
With the roof, yeah.
4 to 5 meters per floor, right? So 30 meter. You see this is 6 times bigger, and they are rotating. It's a big project. And the energy level. This is a Korea nuclear power plant company, and this is their typical reactor. They call APR 1400, and this is a building and arrangement. And 1400 means 1.4 gigawatts of this nuclear power system. So 1400 megawatts, you see. So here you see this is a 10 megawatt. 10 megawatt. This is a 1400. So to replace this nuclear power plant by using a big wind power system, you need to have a 140 of them as a compound of but you see, if you use this size of big ones at the ocean site, it is possible, but depending on the economy, right? But technologically, it is possible to replace nuclear power plant by themselves. It's a huge number. Now, this is NREL, is a short name for National Renewable Energy Laboratory of the United States. They developed more than 10 years ago, 5 megawatt. So this is very popular and famous at the time. The rotor diameter, you see, and this is a DTU of Denmark Technological University. They have a 10 megawatt, and it's a design. Okay? But I guess this is now in commercial market, and this is coming from a PhD thesis, so probably from DTU, and she or still develop a design 20 megawatts. Diameter is almost 300 meters. And you see that Saturn V for the space shuttle or rocket is much smaller than this. And we also see this is a popular home using electrical heater is only used 2 kilowatts, not megawatts. So horsepower, watt conversion, and 1 or 2 kilowatt for electrical heater at home, and 6 megawatt for large wind power. You see this one, and 6, and then gigawatt for commercial nuclear power, and gigawatt for 0.4 gigawatts. So I hope you have some idea on size levels on electricity. And size of wind turbines again. This is very small one, 10 kilowatt, but it's also useful for small island far away. You already, I told you that wind quality at ocean is good. So small island far away, it's not easy to send electricity from the mainland. So it can be a good idea to have a smaller size turbine system for that island, depending on how many people are living. So homes, farms, and remote applications. And using for not only for TV, but also for pumping, telecommunication, ice making. Intermediate size village, not only one home, several homes, and hybrid system, district power, and larger central station, distributed. Oh, this is less. Posted in Denmark.
We humans have harnessed the power of wind for agricultural and industrial purposes for centuries. Today, however, wind is used as an affordable, renewable and climate-friendly electricity source. At Ørsted, we built offshore wind farms across the planet to bring green energy to millions of people. But how does it work? Naturally, a wind farm needs wind to generate energy. So we find locations where wind conditions are optimal, water depths are shallow enough for us to fix the turbines to the seabed, and there is enough space to install hundreds of huge turbines. The largest of our turbines have a rotor diameter of over 167 meters and stand 195 meters tall. The sea winds are captured by their giant blades and transformed into energy inside the nacelle. The rotating blades cause the main shaft to rotate, with a gearbox transferring the rotational speed to a high-speed shaft. This turns very rapidly, which allows the generator to generate electricity by spinning a magnet past coils of conductive wire. This process is known as electromagnetism. The electricity generated from all of the turbines in the wind farm is then fed to a single offshore substation, which then transports the energy to shore via high-voltage cables. Once inland, the electricity is transformed at the onshore substation and fed into the public grid, where it is ready to power the lives of millions of people. Since we built the world's first offshore wind farm back in 1991, we've installed more than 1,200 offshore wind turbines. And for every wind farm we build, we're moving one step closer to a world that runs entirely on green energy.
Right. Question? No. And we move on to next. Lecture reviewed by Cherish online.